Exponential growth and decay. Our objective is to solve problems involving exponential growth and decay. Why learn this? Exponential growth and decay describe many real-world situations, such as the value of artwork. Let's start with some vocabulary. Exponential growth, when a quantity increases by the same rate r in each time period t. Compound interest, interest earned or paid on both the principal and the previously earned interest. Exponential decay, when a quantity decreases by the same rate r in each time period t. Half-life, the time it takes for one half of the substance to decay into another substance. Let's look at exponential growth. An exponential growth function has the form y equals a times the quantity 1 plus r to the t, where a is going to be greater than 0. And now let's look at what our other values represent. R represents the rate of growth expressed as a decimal, and t represents time. So let's practice using exponential growth. The original value of a painting is $1,400, and the value increases by 9% each year. Write an exponential growth function to model this situation, then find the value of the painting in 25 years. So, since this is exponential growth, we're going to have y equals a times the quantity 1 plus r to the t. So we have y equals our starting value, which is 1,400, and then we multiply that by 1 plus, and we would put our rate as a decimal, so we have 0.09, and then to t. So now that we have our exponential growth function to model the situation, let's look at 25 years. So we have y equals 1,400 times 1 plus 0.09, and our time is 25. When we simplify, this is about equal to 12,072 and 31 cents. Now let's look at exponential decay. It's almost the same thing as growth, only it has the form a times the quantity 1 minus r to the t. So it's decay, so we're going to subtract our value from 1, which will end up giving us a decimal. A is still the original amount, r is still the rate of decay as a decimal, and t is still time. So let's try an example. The population of a town is decreasing at a rate of 1% per year. In 2000, there were 1,300 people. Write an exponential decay function to model this situation. Then find the population in 2008. So since we're dealing with exponential decay, we're going to have y equals a times the quantity 1 minus r to the t. And this is a 1, sorry about that. Alright, so we have our original value, which is 1,300, and then we have our 1 minus, and then we want to put 1% as a decimal, so 0.01, and to the t. So that represents our exponential decay function, so we've got our model. And now, let's be more specific. Let's look at the population in the year 2008. So in 2000, we were at 1,300. So are we going to put a time as 2008, or is our time going to be simply 8? Our time will be simply 8, because the difference between 2000 and 2008 is 8 years. So we have y equals 1,300 times 1 minus 0.01 to the 8. And when we simplify, we end up with about 1,200. So the population in 2008 will be approximately 1,200 people. Now let's look at compound interest. This formula is a little bit more involved, but it has the plus similar to that of our exponential growth. So A represents the balance after t years, P represents the principal or the original amount, R still represents our rate, and you express it as a decimal, N is the number of times the interest is compounded. So this piece is the new part, because it's compound interest, so it might be compounded quarterly. And then T still represents time, only more specifically, it's time in years. So let's try an example. So since we're looking at compound interest, we're going to use our compound interest function. So that's our A equals P times 1 plus R divided by N to the N times T. So let's start substituting our known values in. Our original starting amount, what we invested, is $1,000. And we're dealing with things at a rate of 3%. So we have 1 plus 0.03, and then we're compounding things quarterly. So to compound things quarterly, that means it's done 4 times. So our N is 4. And then we have N times T. So we have 4 times 5. And when we simplify, we end up with about $1,161.18. So the balance after 5 years is about $1,161.18. Take a moment and pause the video and try B on your own. When you return to the video, the answer will be revealed below. And there you have it. Now let's look at half-life. Half-life, you have A equals P times 0.5 to the T. Your 0.5, think of it as a half-life. That's where it comes from. So A represents the final amount, P is the original amount, and T represents the number of half-lives in a given time period. So let's practice. Fluorine-20 has a half-life of 11 seconds. Find the amount of fluorine-20 left from a 40-gram sample after 44 seconds. So step 1, we need to find T. So that's our first step. And if you recall, T is the number of half-lives in a given time period. So 44 seconds divided by 11 seconds. So we have 44 seconds divided by the 11 seconds, because fluorine-20 has a half-life of 11 seconds, and we're looking at the sample after 44 seconds. And when we simplify, that gives us 4. So now we have all of the pieces that we need. The original sample you're starting with is 40 grams. You multiply that by 0.5 to the 4th power. And when we simplify, we end up with 2.5. So the amount of fluorine-20 left from a 40-gram sample after 44 seconds is 2.5 grams. Take a moment, pause the video, and try B on your own. When you return to the video, the answer will be revealed below. And there you have it. So there is about 0.02 grams of fluorine-20 remaining after 2 minutes. This also ends our video lesson on exponential growth and decay.